Hello everyone and welcome to our presentation. Today we are going to dive into two fundamental concepts in DS, merge sort and AVL trees. To give you a quick breakdown of how this video is structured, first Adityan K will take you through merge sort, explaining its logic and how it works. Then we will switch over to AVL trees. Sharon here will cover the complete theoretical part and the underlying logic of the tree structure. Finally, I Sumal will take over to guide you through the actual code implementation and how it all comes together. Let's get right into it, starting with merge sort.
I am Adityan K. Today we are going to look at one of the most important sorting algorithms in computer science, merge sort. So what is merge sort? Simply, it's a sorting algorithm that follows something called the divide and conquer technique. The idea is instead of trying to sort a big array all at once, we break it down into smaller pieces, sort those pieces, and then put them back together. It was invented by John von Neumann in 1945, and one of the reasons it's still widely used today is that it always runs in big O and log n time. No matter what the input look like, it's also a stable sort, meaning if two elements are equal, their original order is preserved. Now let's understand the three phases. First is divide. We keep splitting the array into two halves until every piece has just one element. Then conquer. A single element is already sorted by definition, so we don't do anything here. We just let the recursion unwind. And finally, the combine. This is where the real work happens. We take two sorted halves and merge them together by comparing elements one by one and always picking the smaller one first. Now let's go through an example. Say our input is an array with elements 38, 27, 43, 3. First we split it into two separate arrays 38, 27, 43 and 3. Then we split again into each element 38, 27, 43, 3. Each of these is a single element, so they are already sorted. Now we merge 38 and 27, so it becomes 27 and 38 because 27 is smaller. 43 and 3 become 343. Finally we merge 27, 38 and 343. Comparing 27 and 3, we pick 3 first, then 27, then 38, then 43. Final result is 3, 27, 38, 43. Now the array is sorted. When we come to the code, there are two functions. The merge sort function handles the dividing part. It finds the middle, recursively calls itself on the left half and right half, then calls merge. The merge function does the combining. It uses two pointers I and j, walk through both halves and picks always smaller element into the result array. Whatever left over it in either half gets added to the end. Now for complexity, merge sort is big O of n log n in all three cases, best, average and worst. This is one of the biggest strengths compared to something like quicksort, which can degrade to big O of n square. In the worst case, the trade-off in space, it needs big O of n extra memory for those temporary arrays during the merge step, so it's not an in-place sort. So where it actually matters. A big one is external sorting. When you have a file so large it doesn't fit in RAM, merge sort can sort it into chunks from disk. It's also the preferred algorithm for linked list since it doesn't need random access. Python built-in sort and Java's array sort for object both use timed sort, which is a hybrid of merge sort and insertion sort. So every time you code sort in Python, merge sort is part of what's running under it. So let's conclude. Merge sort splits the array recursively down to size 1, then merge everything back in sorted order. It always big O of n log n. It's stable and the only cost is big O of n extra space. It is one of those algorithms that genuinely useful in practice, not just in theory. Thank you.
So, my name is Sharon. I'm going to talk about AVL Trees, which is a self-branching binary search tree. AVL Trees are used to maintain efficient searching, insertion, and deletion operation by keeping the tree balanced. In this seminar, we will discuss about why AVL trees are needed, balance pattern, rotation, and the time complexity. So, before understanding AVL trees, let's first understand the basic idea behind balanced trees. In data structure, the efficiency of searching depends heavily on height of the tree. If the tree becomes too tall or skewed, operation becomes slower. AVL tree solves this problem by maintaining balance automatically. What is an AVL tree? AVL tree was introduced in 1962 by Edelson, Wilsky, and Landis. It is the first self-balancing binary search tree. In an AVL tree, the difference between height of the left and right subtree of any node is at most 1. Because of this balancing property, AVL tree maintains efficient performance. Let's talk about the need for balancing. This slideshow shows the main problem with a normal binary search tree. If elements are inserted in sorted order, the binary search tree becomes skewed. Instead of looking like a tree, it starts behaving like a linked list. As a result, searching time increases from logarithmic time to linear time. AVL tree prevents this problem using balancing operation called rotation. Now let's talk about balance factor. To maintain balance, AVL tree uses something called balance factor. Balance factor is calculated as height of the left subtree minus height of the right subtree. For a valid AVL tree, the balance factor of every node must be either -1, 0, or 1. If the balance factor becomes greater than 1 or less than -1, the tree becomes unbalanced. For rotation cases, whenever the imbalance occurs, AVL tree performs rotation to restore balance. Four types of rotation are LL rotation, left-left rotation, RR rotation, right-right rotation, LR rotation, left-right rotation, RL rotation, right-left rotation. A single rotation, the LL and RR rotations. In LL rotation, imbalance occurs in the left subtree of the left child. This makes the tree left heavy. To restore balance, we perform right rotation. In RR rotation is the opposite case. Here imbalance occurs in right subtree of right child. So we perform a left rotation to balance the tree. So let's see an example of LR rotation. Here we can see that insertion occurs in the left subtree of the left child. As the nodes are inserted toward the left side repeatedly, the tree became left. The balance factor of the top node is greater than 1. So the tree became unbalanced. To fix this imbalance, we perform a right rotation. Here I am performing a right rotation from middle node to the root node. So the middle node becomes the new root node and the previous node moves to the right side. This restores the balance while preserving the binary search tree property. So let's see an example of RR rotation. Here the insertion occurs on the right side of right subtree of the right child. The tree became right heavy. To fix this RR imbalance, we perform a left rotation. The middle node becomes the new root node. Now let's talk about double rotation, LR and RL. Sometimes single rotation is not enough. In LR rotation, imbalance occurs in the right subtree of left child. So the first we performs left rotation and then right rotation. Similarly, RL rotation requires first right rotation and then left rotation. Let's see an example of LR rotation. Here the insertion occurs in the right subtree of the left child. So the imbalance is not directly outside, it occurs inside subtree. So first we perform left rotation on the child node. This converts LR case into LL case. Then after the first rotation, the tree structure changes to simpler LR imbalance. Now we perform a right rotation on the parent node. The tree becomes balanced again. So therefore LR rotation becomes first left rotation, then right rotation. Here is an example of RR rotation. Here insertion occurs in the left subtree of the right child. So first we perform a right rotation on the child node, then convert RL case into RR case, now we perform a right rotation on the parent node. Then the tree becomes balanced again. Therefore, the RR rotation requires first right rotation, then left rotation. Now we can compare the performance. This slide compares the performance of normal binary search tree and an AVL tree. The main advantage of AVL tree is that it maintains balance automatically. Because of this, the tree height remains small, which improves operation speeds. First one is search operation. In normal binary search tree, worst case search complexity can become big or often. This happens when the tree becomes skewed like a linked list. But in AVL tree, balance keeps the height logarithmic. Therefore, searching in AVL tree takes logarithmic time. Next one is insertion operation. Insertion in normal binary search tree can also become big or often if the tree is skewed. In an AVL tree, insertion includes balancing operation called rotation. Even after rotation, insertion remains logarithmic because height stays balanced. Next one is deletion operation. Deletion in AVL tree is also logarithmic. After deleting a node, AVL tree may perform rotation to restore balance. Next is space complexity. Both binary search tree and AVL tree requires linear space because every node must be stored. However, AVL tree stores extra information such as height or balance factor for balancing. Next is real-world application. AVL trees are used in many real-world applications. They are used in database, memory management, file system, and search engines. These applications require fast searching and efficient data organization. So that's all. Thank you.
I want to say this one as avl.c, I guess. Okay. So as usual, include the header file. Include the header files as hashing standard input_output.h. Then structure of a node. So the structure of a node, here it is. See here, a structure of a node consisting of here 4 partitions. Generally in a binary tree, a node consisting of 3 partitions. One is pointed to the left, one is pointed to the right side, and another one is data. Now including these 3, we will store another information, that is height of that node. So that means totally how many partitions are present in a node? Now instead of 3, we are taking 4. Why? Because binary search tree only left, data, and right. In AVL trees, so this is depending on entire thing, here height. So that's why we have to store that height of a node in each and every node, please. That's why a node consisting of here 4 partitions. Okay, right? So now we will define structure of a node. So one is data partition, the one is left pointer and right pointer. So struct node star left comma star right, and height we can save it as an integer variable, store it as an integer variable, and we can name it like ht. After structure we have to put semicolon. So semicolon. First we will write height function. So how to find out height? So for height function I am taking the function name as height. So height of a node we want to calculate, so that's why struct node star sum, and I have taken. Okay, then if that node is null, if that node is null, then there is no height of that node. Okay, so just return 0. Otherwise what we have to do is whatever the data present in that height partition, that height we have to return. That means, so here whatever the data present in this, that we have to return, that will be returned, that we are doing in height function. Now we have to find out maximum heights. So why? Because so what is the left subtree height and what is the right subtree height, that we have to do now. So here this is 3. If you have consider, we have to compare. So which one is maximum? One is integer sorry, integer a comma integer b, then return. We can use a ternary operator for simplicity purpose. If a greater than b, I think if a greater than b, then a, otherwise b. So that is maximum of 2 numbers. Then we have to find out balance factor. So now balance factor is height difference between left and right. Okay, so find out balance factors. So it has to return a value. Why? Because balance factor is an integer, so height difference between left and right, that's why here it has to return an integer. So balance factor of struct node star and sum n, that is some node. Okay, if that node is null, then we have to return 0. That is the balance factor, right? So otherwise, suppose node, if the node is existing, then we have to find out balance factor. So we have to return like height difference between height method. What is the height method we have taken? So capital H. So for I'm taking small h. Okay, if node is, we have to find out the balance factor, which is height difference between left and right. So call the methods height of the nodes left minus height of height of n of left, then height of n of right. So heights of left subtree minus heights of right subtree is nothing but your balance factor. So now close this one. That is balance factor. After balance factor, what we will do? Simply we can write rotations. We can write easily. So now rotations, or directly we can write insert method. No problem there. In insert method, we'll call all these methods. Now, so I'm gonna write first rotation struct node star single left rotation. So here I could say struct node star some y or some a, or we can put some pointer, right? So like just put here, right? So now struct, if you observe, take one example here. For the example, see here 10, 7, already some element is there. Here some 20, and here some element is there. 7 greater means you may get 9. Okay, for example, here there is no element. So now here we have inserted like 5. So this is the new element we have inserted. And okay, then what we have to apply? Single left rotation we are applying. See, we are rotating toward right side, but now what I am assuming is, so the arrow mark is from left to right. I am taking single left. Some other, here what is going to happen? Here the properties failed bit here. Then 7 will become root node, 10 will become 7's right child, and where we are getting point of modification. So actually before rotation 10 is left is 7, but after rotation 7 right is becoming 10. Okay, so 7 is left as it is. For example, if here any other node is there, that here we will get. Okay, so that's why here if it is a PTR, take this as some X, take this node as some T2. Okay, then what is happening? X is becoming root node. X right, this is our PTR getting yes, right, X of right equal to PTR, then PTR of left equal to T2, then we are getting this one. Then after rotation we had to find out again balance factors. That means not only balance factors, heights we had to update. Why? Because heights are changing, right? So we have to update the height also. Okay, so we'll add that same here. Now struct, so we are assuming this as some X and this as some T2. Now we will declare and initialize node star X equal to, so what is X? X is nothing but PTR left, right? So PTR PTR to the left. Then what is here? Y T2. T2 is X, right? So same declare here node star T2 X to the right. So assume this as Y instead of right in here. Here we can write Y also, right? Now we have to change the links. Now we are changing the links. X of already here I have mentioned right, X of right equal to PTR and Y to the left equal to T2, and then we had to update the heights. So Y to the so Y is height, we have to update the height equal to maximum of height of Y to the left subtree, right, and height of Y to right, whichever is the maximum. For that +1, we have to update the height of X also. X of height equal to here we can just copy paste it and change the part where Y to X. So finally we just becoming root node. Finally X is becoming root node. So finally return X. Okay, for single right rotation also the same thing. Struct node star single right of struct node star X. Okay, now the same thing, YT2 we have to declare star Y equal to X to the right. Okay, and then node star T2 equal to Y to the left. Now similar to single left rotation, here single right 20, 30, 40 for example. Here the properties failed. Assume that as X. Now assume this as Y. 30 is becoming root node, right? 30 is becoming left side for Y. And this is some temporary node. If it existing here, we will get the modification. we may get doubt why we are taking this. Yeah, after rotation this node will the position of this node also changes, right? Yeah, so 40 30, yes. Here we are getting modification. For example, here the node is 25, 30 is left is 25, but after rotation where we will get 25, we will get 25 as 20 is right side. So that's why this also we have to take as one another node similar to here. Okay, so that's why we are taking two additional pointers. Now coming to the program. So then after rotation the links are modified. So here I am writing y to the left x to the right equal to 2, and then we have to update pointers x right equal to maximum of height of x to the left comma height of x to the right plus 1. Okay, so now let's copy paste it, and we can change the part where x to the y. So now close this. So that is single right rotation. So now after single left and single after single right rotation, left and right single rotation, we can call insert method. So let's implement insert method. Struct node star insert struct node star pointer ptr int data. Which element we want to insert? Instead of data, here we can take it as some element. Okay, so now we are going to insert. This is similar to binary search tree, and then we will check balance factors. Okay, if ptr equal to, if there is no node, then it will be null, right? Then what shall we do? Allocate memory for that node. Struct node star. So here we are allocating memory for node, right? So ptr equal to, we can typecast here struct node star, then memory allocation malloc methods str size of struct node circle. Now we have to insert a data, right? ptr to the right, sorry, ptr to the data equal to ptr to the left, ptr to the right equal to null. As they are leaf nodes, then left and right pointers, and okay, then we have to write the height of the node. So ptr of height equal to 1, and then return ptr if the node is not present. If the node is present, we have to insert based on less or greater. If it is less, then insert on left side. So ptr of left equal to insert of ptr of 2 comma uli, and else if it's not less, it may be greater. If element is greater than p of right, then this is similar to binary search tree program. Okay, in binary search tree program also we have done like this. So PTR of right equal to insert of PTR to right. Right. Come on, right. After that, after insertion, we have to update that height of that node. Same thing here. Whatever here we are written, same thing here we have mentioned by. Here we will mention PTR symbol. PTR. So after insertion, that height will be updated. PTR of height we have updated. So after calculating height of that new node, we have to find out balance factors. If balance factors are not satisfying the property of an AVL tree, then we have to apply rotations. Okay. So first find out balance factors. So balance factor integer, like if I'm writing balance factor equal to here balance factor function we have considered this one, balance factor of which node, that a new node PTR. So after getting balance factor, check the conditions. If balance factor is greater than 1 and element is less than PDS left of data, okay, then which rotation we have to apply? Single left rotation PTR. Okay, suppose if balance factor is single rotation, first I'm writing single rotation and element is greater than PTR to the right. So yeah, return. First I'm writing single rotation, now so call that single right of PTR. Now in left side we have inserted this, right? Then what shall we do? So if this failed, so that's why we write the same condition here. On left side we have inserted, so it's not satisfied. Then which rotation we have to apply? Double rotation. Which double rotation we have to apply? For first apply single right rotation, single left rotation. So PTR of left got to single right rotation at PTR left. After applying single right rotation at PTR, we have to apply single left rotation. So simply we can write return of single left rotation. At single left rotation, simply here right, double right rotation. Double right left rotation is nothing but first single right and then single left rotation. This double rotation. Now another condition, if you want to apply double left right rotation, the condition is similar to this one, but this condition is failed. Is here it is less than, then double left right rotation we have to apply now, so that we will call here. Double left right rotation means first single left and then single right rotation. Single left rotation we have to apply on right side. Left rotation we have to, yeah, on the right side. and then single left rotation. Single left. Right there we have applied 4 rotation. This is single. This is single right. This is double left right rotation. So finally we have to return PTR. That's it. So this is insertion function. So then we have to display the elements. Void in order of struct node star PTR. If PTR not equal to, so in order means left root right. Okay, printf percentage d, give some space here, and PTR of data left root and then right root in order of PTR right. So first we will check in order. If it works, then we will check pre-order and post-order display. Okay. Void main function. Declare the variables struct node star PTR equal to. So initially 370, so now we call insertion method one by one. Set of PTR comma several insertions will check. So here it is 10 here. Several insertions. Then let's make it 5, 20, 50, 80. Now we will display. Should have the in order traverse is in order PTR. So here you can write int actually. If it's integer, then return 0. Now let's save the program and compare and execute. Semicolon is missed here. Errors are coming, just rectify it. Okay. Okay, now the inverter is working. Now we can check post order. No, sorry, inverter and post order. And post order we will verify it. So in order, this is pre-order, so it means root left right. So function name is pre-order. Pre-order. Plus we will get this one. Yeah. Post order. Post order. Post order. Now here we will call. So now run the code. So as see, default in order traversal elements are in ascending order. So it's correct. So this is AVL tree program. I hope you understood the video. That's it.